Okay, okay.
Good morning, sir.
Good morning.
So,
Good
good
morning.
mo- good morning, sir. Good morning and welcome to all. I, Dr. Krishna Kumar, Assistant Professor in Department of Industrial Engineering, IERT Prayagraj. It's my distinct pleasure to introduce and welcome today's resource person, Honorable Professor Harnath Kar, sir. Professor Karsar is working as a professor in Department of Electronics and Communication Engineering, Motilal Nehru National Institute of Technology, Prayagraj. He completed Bachelor of Engineering from Indian Institute of Science and Technology, IIEST, in 1989 and Master of Technology from Banaras Hindu University, now IIT BSU, in 1992. He completed Doctor of Philosophy from University of Allahabad in 2000. His area of research interests are 2D systems, digital filter, digital signal processing, nonlinear dynamic system, delay system, robots control, model reduction, and multi-dimensional system. Professor Cursor is having more than 20 years teaching and research experience at UG and PG levels. He published 90 papers in reputed journals, including 74 SCI, 8 Scopus, and 8 peer-reviewed journals, also 18 conferences. In the overseas assignments, the Professor Cursor worked as an assistant professor in the Department of Electrical Electronics Engineering, Altılim University, Ankara, Turkey, in 2002 to 2004. He attended Industrial Pneumatics Symposium organized at SMC Pneumatics Ltd in 2007. He also participated in the Leadership for the Academician program organized by IIT BSU in collaboration with the Penn State USA in 2019. Professor Cursor received various awards and honors, including the receipt of 2002-2003 IEEE Heaviside Premium Award UK, receipt of D.N. Agarwal Award of Excellence in 2005, secured 10th rank in India and 1,367 worldwide in the subject area of networking and telecommunication system, according to independent study conducted and published by Stanford University, USA in 2020. Professor Cursor also served as a reviewer for many international journals and conferences, including IEEE Transition on Signal Processing, IEEE Transition on Circuit and Systems, and many more. He served as a member of editorial board of the Journal of Mathematical Problem in Engineering, Hindavi Publications, Journal of Engineering. Once again, I welcome Professor Sir for the today's session to enlighten her experience, knowledge with us. Thank you, sir.
Thank you. So first of all, I used to congratulate Department of Electronics IERT Degrees Division for conducting such a nice program. And I am thankful to Dr. Jotindra Gaurav, Head of Electronics and Communication Engineering Department, IERT, for giving me this opportunity to deliver a talk on this faculty development program. I am also thankful to Chairman Dr. Bimal Mishra ji, Director of IERT, and organizing committee members of this faculty development program for their effort and giving me an opportunity to talk to this, to interact with you people. Thank you.
Thank you, sir.
Is my screen is visible? No.
No, sir.
Okay.
No.
Okay, I'm trying. Is it visible now?
Yes, sir, visual.
Okay.
Sir, visual.
Okay. Okay.
Okay, sir.
Okay. So in this lecture, actually, we will discuss about fault detection in digital circuits. So you know that when we implement one digital circuit, so it may suffer several types of faults. So for the proper operation of the circuit, we must detect whether there is any fault or not. So main purpose is to determine whether a given circuit operates correctly or not. So in this lecture, we will discuss about various types of faults which may occur in the circuit and how to detect them. Okay. So first, you see the types of faults. Generally, the digital circuits, they suffer two types of faults. Some faults are temporary in nature and some faults are permanent in nature. Temporary faults are due to the non-ideal behavior of the logic gates. They occur due to noise, or actually while designing the circuit we assume that the propagation delay of all gates are 0 or they are identical, but in practice the gates have all gates have gates have some finite propagation delay. For example, standard in case of standard TTL it is 10 nanosecond, and even if you choose two gates from the same logic family, their delays are not exactly same. For example, instead of 10 nanosecond, it may be 9.99 nanosecond, or maybe 10.0001 nanosecond. So there will be some mismatch. In practice, the delays are not actually, they are of the same order, but they are not exactly same. So due to this, some temporary faults you can, if you do not design the circuit properly, so some undesired output, the circuit may show some undesired output. So these faults are temporary in nature, they will not be there for longer time. Momentarily, in the form of glitch, you may get some temporary faults in the circuit. And some faults are permanent in nature, they occur due to component failures, and these faults will remain there until and unless you repair it. Now we'll study the transient phenomena by taking one simple example. Suppose we used to implement one switching function of three variable, f of x, y, and z, function of three variables x, y, z. Okay, and in sum of product form, it is min term m2 plus m3 plus m5 plus m7. So how we design it? We plot the function on a K-map, And you see that in the diagram that K-map is shown. And if you plot it, okay, so XY variables are given one side, Z is another side, and we have just plotted the function. Now we can simplify the function in a manner by pairing the adjacent cells. So function will be x bar y plus xz. Now suppose you are implementing this function using two level and OR. And implementation is shown. We can implement it using two NAND gates and one OR gate. Now here what happens? Suppose initially, suppose we are applying y equal to 1, y equal to 1 and z equal to 1. Okay, y equal to 1 and z equal to 1. And x is 0. That means it corresponds to x is 0, y equal to 1, z equal to 1. So output should be 1. Now suppose x is changing from 0 to 1. So if x changes from 0 to 1, so xy will change from 1 to 0. And you see that the gate output of gate 1, it will also make a transition from 1 to 0. And output of gate 2 will also change from 0 to 1. Now what happens if the delay, suppose delay of gate 2 is more than delay of gate 1, then momentarily for some time you will get incorrect output 0, because the output of gate 2 0 to 1, because the delay of gate 2 is more, then the propagation delay of gate 2 is more than propagation delay of gate 1. For example, if you assume that delay of gate 2 is suppose 20 nanosecond and delay of gate 1 is suppose 10 nanosecond, then what will happen after 10, immediately after 10 nanosecond, the output of the output F will be 0. You can simply verify it. And after 20 nanosecond, what will happen? Output will again reach to logic 1. So momentarily we are getting one incorrect output. You see that ideally we should get at the output of this circuit, it should maintain logic 1 level throughout. Because if x equal to 0, y equal to 1, z equal to 1, output is 1. If x equal to 1, y equal to 1 and z equal to 1, then also output is 1. But while x is changing, at input x is changing from 0 to 1, okay, due to finite propagation delay of logic gates, you may get incorrect output between two correct outputs. So output sequence is 1, then momentarily it will be 0, then again it will be 1. And you see that this 0 is the incorrect output. In between we are getting 1, 0. But ideally the circuit should maintain logic 1 level at the output. Now this momentarily output, this is the incorrect output, and it will not remain there. You see that after 20 nanosecond, actually 20 nanosecond is the delay of the gate 2, propagation delay of the gate 2. The output will again be, it will correct itself. So this is actually temporary fault. And the output pattern is 101. Actually, this pattern you will get if in case of two level and or realization. Okay. Now, so the output of combination circuit may take a transition even though the pattern supplied at its input does not imply change. These unwanted switching transitions are known as glitches. Okay, these are the glitches. And if there is a glitch in a circuit, we will say the circuit has hazard. Now, first we'll discuss about static hazards. Static hazards, just in the previous example, we have seen that output pattern, that 0 is the correct output, 1 is the correct output before the change of the variable x, and 1, the last one in this pattern, the last one. This is the correct output after the change of the input variable x. And in between, during the transition, we are getting one incorrect output 0. So this, if output pattern is 101, that is known as static 1 hazard. This one in this diagram you see, a timing diagram, 101. So first one is before the change of the variable, last one is after the change of the variable, and in between we are getting one incorrect output. And this is due to the non-ideal behavior of the gates. This is transient phenomena, temporary in nature. Similarly, this static one, this kind of hazard can occur only in two-level AND OR realization. Two-level OR AND realization, static one hazard is absent, because actually how we realize the function in AND OR using AND OR gates, two-level AND OR gates. We actually simplify the function, we plot the function in the K-map, and we consider the cells which contains ones. Okay, so so here actually when we have shown one arrow, actually we are getting hazard. You see that this in the K-map we have shown one arrow. Actually during this transition, actually we are getting incorrect output. So here actually because we are considering the cells containing ones, so in case of two-level AND OR realization, static 1 hazard is possible, static 0 hazard is not possible. Similarly, for static 0 hazard, if you simplify the function using the cells containing zeros, which we do for OR AND realization, then output pattern will be like this: 0, 1, 0. 0 is the correct output, and correct output before the change of its variable. The last 0 is also correct output after the change of the variables, and we may get momentarily one output in between during the transition of the input variable. That is, static 0 hazard may occur in OR AND realization. Okay. Now, we can say that if static two-level AND OR realization is free of static 1 hazard, then it is free from any kind of hazards. Similarly, if two-level OR AND realization is free of static 0 hazard, then it is free of static 1 hazard, any kind of hazard in fact, because this is the only hazard which can occur in two-level OR AND realization. Okay, so if you can make the circuit free from this hazard, circuit will be hazard free. Now, static hazard actually it occurs due to single input variable change, and it may cause momentarily incorrect output. Actually, output should remain constant, but due to the single variable change, momentarily it can produce incorrect output. That is static hazard. And this static hazard occurs during minimal realization of digital circuit. Minimal realization means when we are trying to simplify the function. So during simplification, if there are any uncovered cells, uncovered adjacent cells, then those cells may create problem. So during that transition, hazard can occur. So how to eliminate the hazards? You see that this in the K-map, we have this is the previous same example. What we are doing, we are using some redundancy. We are introducing some redundancy. We are the red major cells, adjacent cells, we are covering that also. So it will give you one additional term in the simplification. Actually, simplified expression was x bar y plus xz. But when we consider these pairs, yz corresponding to this yz. So if we add this term, if we consider this term, then the circuit will be hazard free. You see that if y equal to 1, z equal to 1, and if x changes from 0 to 1, now that problem is not there, because we are using one additional gate yz. So y is 1, z is 1, so output will remain 1. So it will not produce any kind of glitch. So static hazard, you can eliminate static hazards by introducing some redundancy in the circuit. So here actually we have to consider this term also, YZ. Then it will be free of static hazards. Then dynamic hazards. Actually, dynamic hazards occur in multi-level realization. More than if we implement the function using more than 2 levels. So in case of 2-level relation, you will get static hazards. The pattern will be either 101 or 010. But in case of dynamic hazards, it occurs actually the output will make undesired transitions more than once. The pattern will be like 1010, the first diagram, or it may be 0101. So this kind of hazard actually occurs in multiple. If you realize the circuit using multiple levels, more than 2 levels, then it will be subjected to dynamic hazards. So you can see how to eliminate these hazards. If you can consider 2 levels and eliminate all static hazards in that circuit, then it will be free of dynamic hazards also. Now, from design point of view, you see that what designer wants. Designer wants 2 things. The circuit should be simple, low cost. Simplicity of the circuit is one factor. Another factor is reliability of the circuit. Simplicity tells us that use less number of logic gates, use minimal realization. Okay, but minimal, if you realize the circuit in its minimal form, but minimal forms are most vulnerable to hazards. Hazards may occur in that circuit. And reliability means there should not be any hazard. So to have hazards, what you have to do, you have to introduce some redundant gates. Okay. So you have to make a trade-off between these two. You have to study whether that glitches will, due to those glitches, the circuit will malfunction or not. Whether those glitches, suppose if you wish that, okay, we will take output after some time. So even if there are some glitches, it is not going to malfunction or incorrect output. So in that case, you can allow that. So the designer has to take care of simplicity as well as reliability. The circuit should be simple, but it should be reliable also. Okay, so there should be some trade-off during this kind of relation. Okay, so far we discussed about temporary faults. So temporary faults are not permanent in nature. They will occur in the circuit momentarily. Now it depends on application, which kind of you are designing the circuit for which type of applications, whether those glitches will cause any problem or not, whether they are acceptable or not. So depending on that, you can choose where your design philosophy for designing the circuit. Okay. Now, so to eliminate hazards, what you have to do, there should not be any uncovered cells. It may be pairs or quads or active. Adjacent cells should be covered. Then, then the circuit will be free of hazards. Next, we will move to permanent. This is more important. Permanent faults, because permanent faults will be there. So you have to repair it. Until and unless you repair the circuit, the fault will remain there. Okay. So why do we require testing? Why fault detection or testing is needed? Now what happens when we design the circuit during manufacturing? So during design, some errors may introduce. It may be human error also. You have not taken some factors. Maybe you have not considered the effect of temperature while designing the circuit, or many other factors. You have ignored some factors during design. So in practice, you may see that it is causing some problem. So errors during the design phase including human error. Or during synthesis, designing, suppose you are using some software tools. Now, don't think that software tools are 100%, it may not be correct. There may be some bugs. So bugs during synthesis, maybe in the software CAD tools or any other software which you are using. So you need testing. After synthesis, you have to test whether the circuit is operating correctly or not. Even faults may occur during fabrication, IC fabrication or packaging. So faults may occur. So we need actually testing is required to avoid these things. So simply we have designed the circuit, don't think that it is going to work properly. And you have experienced it. So if you implement some circuit on breadboard, oscillator or any kind of circuit, you may see that the circuit, even if your circuit is correct, it is not working. There is some problem. So we need to test it. Okay. And nowadays, VLSI chips, actually there are numerous transistors. So possibility of faults is also more. It is also significant. So testing is used to detect the presence of faults in a given circuit. That is testing. Now here one thing, here there is a fallacy. Fallacy is that no amount of testing can ensure, give guarantee that circuit will be free of all kinds of faults. Because there may be some faults which are physical defects, in fact, mechanical defects due to the faults or errors are mechanical in nature. So those are actually we normally do not consider. So no amount of testing can give you 100% guarantee that circuit will work properly. But still testing is required because it will give you, if you increase the confidence level, maybe that you cannot guarantee 100%, but you can guarantee 99%. So by testing, we can boost our confidence in the correct working of the circuit. Okay, so if you perform the test, so you can say that yes, it is 99.9% that it will work properly. 100% batana muskil hai, but the chance or confidence level of the designer will increase if you perform certain test. Next, when to do testing? Now, testing can be done at various levels. First is chip level testing, when chips are manufactured. Okay, board level, when chips are assembled on boards, and system level, when system boards are assembled together. To develop a system, several boards are assembled together, so you can perform the testing at system level. But here, what happens, even if you have experienced this thing, suppose you are going to implement some circuit in your lab. Okay, so first what you should do, first you should check all the wires, whether there is any disconnect, they are disconnected or not, whether the breadboard is okay or not, if there is any short or open circuit. Two lines have been shorted, that you have to check using maybe multimeter or anything. So then you should check the ICs, whether the ICs are okay or not, using IC tester. Okay, so if you perform your experiment in this way, then you will see that most likely the circuit is going to work. And if you blindly if you make connections, it may not work. And later on, the complete circuit you will give that to teacher, or it will be very difficult to find out the fault. Okay, so what I mean to say, that it is easier to check the to detect the faults at chip level rather than system level. Now, rule of thumb is that early detection of fault reduces the cost of testing. Okay, and second point is that rule of thumb, that it is 10 times more expensive to test a digital system as we move to the next higher level, chip level to board level to system level. So it is always preferable that you perform testing at chip level, then go for board level, then go for system level. If you start at system level, it may take more time and the cost of testing will be more. It will be expensive. Next, the problem in fall detection. Actually, the number of possible faults or number of possible defects, they are in fact numerous. Okay. So what we do, actually, we just analyze the physical defects depending on our environment or the under which condition the circuit will work or nature of the circuit, and we model the faults, construct some fault models. That okay, we will check these kind of faults. These are the possible faults here. But that set of faults that may not cover all the faults, all the possible faults. Okay. So a fault model is required. We'll discuss about fault model also. Fault model identifies some target. We set some targets. So okay, we will check these things, these faults. Of course, it will reduce the. It will increase your confidence level if you check those faults. A fault model makes the analysis possible. Otherwise, because the physical defects, it is actually uncountable. It is nobody can guarantee that they are बस इसमें यही फॉल्ट होगा, इससे बाहर जो है नहीं हो सकता है, ये कहना बहुत मुश्किल है. ओके, सो आपने एक सर्किट मान लीजिए डिजाइन किया, फिर जो है आपने सारे ये टेस्टेड एवरीथिंग, और क्या हुआ कि ओपन में क्या होगा, बारिश हो गया. आप कैबिनेट जो भी जो था उसका आपने ध्यान ही नहीं दिया, है ना, सर्किट इज नॉट वर्किंग. तो देयर मे बी मेनी थिंग्स, है ना. ये डिजाइन सर्किट, आप टेम्परेचर वहाँ पे रिड्यूस होता है, -40 डिग्री चला गया. आपने जो डिजाइन किया तो उस टाइम पे उसमें ध्यान ही आपने नहीं लिया है. तो इस टाइप का फॉल्ट्स जो है उस टाइम पे तो सर्किट करेक्टली काम नहीं करेगा. नाउ वी define one parameter known as fault coverage. This is interesting. The total number fault coverage is defined by number of detected faults. Whenever you are testing the circuit, you have detected some faults. Okay, your circuit, the testing is, while testing you have taken care of some kind of faults. So number of faults detected, number of detected faults divided by total number of possible faults in the circuit, है ना, into 100%. So that this is actually fault coverage. So even if you cover 80% faults, that is good. Next, we will go for fault models. Now, to reduce the complexity of test generation, one need to model the actual defects, actual physical defects. Okay, that may occur in the digital circuit. So we will model the faults actually, that is fault model. Some models, we will use some models for physical defects or possible faults. Now, structural fault models. The fault models are of various types: switch level fault models, structural fault models. These are the popular fault models which we use, mostly widely used. Okay, structural fault models. So it is very useful for digital circuits, combinational circuits, or maybe sequential circuit also. Any kind of digital circuits at gate level. This is gate level testing. Now, what we do in tactile testing, we will guarantee that interconnections are okay. The wires or lines, interconnections of the structure of the digital circuit, they are fault free. Now in digital circuit, what happens? Each wire, it will be either at logic 0 or at logic 1. Accordingly, in this fault model, we consider two types of faults: stuck at 0 fault and stuck at 1 fault. Stuck at 0 means the line is behaving always, it is at logic 0. Okay, somehow it has been stuck to 0. It has been grounded. It is not necessary that always it will be grounded or always it is connected to supply. Actually, even if suppose if there is a cut in the line, So if you are using suppose TTL logic, in case of TTL open terminal, it assumes logic 1 value. So here actually not exactly that line has been connected to plus VCC, but because it is open, it is logic 1. So this stack at 0 model and stack at 1, this fault model, it considers whether the line has been shorted, grounded, or it has been connected to the power line, or there is any cut in the lines, other cuts or shorts in the line. So so this is this model is widely used, and this is popular model, and it works also. Performance is good. So this is structural testing. So structural testing, the basic objective is to guarantee that interconnections are okay, fault free, and they are able to carry logic 0 or logic 1 signals properly. So even if you guarantee this thing, so there is you will get a lot of confidence that circuit will work properly. So this is good, and it is widely used. And another types of model which is mostly used in switch level fault, switch level to detect faults at switch. Switch means transistor switch. So switch level models are concerned with the faults in transistors and interconnections. And this type of fault models are widely used with most technologies, in particular with CMOS technology. Now here fault models are actually normally we consider three types of faults. Stack open fault. Stack open fault means it refers to the situation where a transistor has been permanently off, non-conducting. A transistor is suppose it is subjected to some fault, so that is stack open fault. So due to some defect, the transistor is not conducting. It is always not conducting. That is stack open fault. Stack on fault or stack short fault, the transistor, it has been permanently on, conducting. Okay, so that is stack open fault. Then bridging faults. In the circuit, two or more distinct lines, the lines are separate, but somehow they have been shorted due to faults, due to some defect. Two or more normally distinct lines, they're supposed to be separate, they should not be connected, but they due to physical defects, they have now been connected due to fault, or they are shorted together. That is bridging fault. Now input bridging, if there is short at input, so it can form OID logic, OID and logic. Okay, and if there is suppose somehow the output terminal has been connected to input, that is feedback bridging. So due to feedback, the circuit may produce oscillations. It can cause oscillations, or it can form latching of latch means additional memory. If output is shorted to input, so yeah, this kind of undesired things can happen. It may lead to oscillations or latching phenomena. Latching phenomena means it will act as memory element. Okay, so these are the problems with bridging. Next, we'll consider some methods which are also used in the context of testing of fault detection for combinational logic circuits. So there are various methods. So I will just introduce three methods, and the purpose is to give to introduce the concepts to behind these kind of fault detection methods. Okay, so first one is fault table method. Then we'll discuss path sensitizing method, then Boolean difference method. So objective is that circuit is given to you. For example, suppose half adder circuit or full adder circuit, it consists of several logic gates. Okay. Now, by doing some experiment, we have to determine whether the circuit is operating correctly or not. In fact, we do it in the lab. We do it. Suppose you have implemented on half adder circuit. Then what we do, whether the circuit is operating correctly or not, what we do? We verify the truth table. We simply write the truth table that X, Y, Z, these are the X, Y input and sum and carry output. So apply 0, 0 and we check S on sum and carry. And if the output matches with the truth table, output of the given circuit matches with the truth table, we say that yes, it is working perfectly well and it is okay. The circuit is good. Okay. Now, what happens if suppose number of inputs 10, then you need to, then size of truth table will be 2 to the, it will have 2 to the power 10 rows, that is 1024. If you have suppose 20 primary 20 inputs, so you need to test 2 to the power 20. A truth table size will be 2 to the power 20. There will be 2 to the power 20 rows, and that is a huge figure. You can calculate it will be more than 10 lakhs. 1000 into 1000, 1024 into 1024. Okay. So if there are 50 lines, so the size of the truth table will be huge. So truth table verification is okay for the small circuits. If it is the size of the circuit is very small, it consists of suppose 4 or 5 inputs, then it is okay. But if it is it consists of suppose 20 inputs or 50 inputs, it is not actually physically possible to test the circuit. So that is not the feasible solution, truth table method. Okay, but that is also one method, and it works. It is suitable for small circuits. So that's why we will see that whether we can find out a subset of those tests instead of 2 to the power n test for the input circuit. Can we reduce the number of tests? Test, what is test? Test is nothing but the application of one input combination, that is test. The input which will apply, that is known as test. Okay. So, okay, we'll move to this table. Suppose left side you see that there is one circuit. It has only 2 gates. Inputs are A, B, and C bar. And if we use stacked fault model, so we are assuming that the lines will be either at stacked 0 or stacked 1. Now we are considering 4 lines. Suppose this M, N, P, Q. The line or where, right? So M may be stacked 0 or 1. So we normally use the notation M0. M0 means that the line M is stacked 0. M1 means M suffix 1. That is, the line N is at stacked 1. So we will this kind of notation we use. So we are considering 4 lines M, N, P, Q. Now each line can be either in stacked 0 or stacked 1. So accordingly the circuit may be subjected to 8 faults. You can consider the output line also, where F is written, right? Output of gate 2, you can consider that also. Then you will have 5 wires and each wire can be at stacked 0 or stacked 1. But in this particular example, we have assumed that the output line is, there is no fault at the output line. So we are considering only 4 lines, M, N, P, just to इसका साइज को थोड़ा कम करने के लिए. If you wish, you can consider that also. You try to understand the procedure. So here we have input variables are A, B, C. So in the right hand side, we have written the input variables. This is basically truth table, and F is fault-free output. The output of the circuit if it operates properly. So that is actually truth table. F. Okay. So output function is AB plus C bar. So you see that when input combination is 0, 0, 0, the output will be AB plus C bar. So output is 1. So in this way we have for 0, 0, 1, the output will be 0. Just you calculate the output F equal to AB plus C bar. So you perform AB plus C bar for different input combinations. You will get the fault-free output F. Okay. Next, what we will do, we will calculate the outputs in presence of faults. Notation is to say actually M0 means line M is at stuck at 0. M1 means line M is at stuck at 1. And we have used the notation FM0. FM0 means F actually output. F is the output in presence of M0. That means output when line M is at stuck at 0. Okay. Line M is at stuck at 0. So you see that if line M is stuck at 0, you just see the expression F equal to AB plus C bar. Okay. Now if line M is stuck at 0 means that input variable A, as if input variable A is 0. So in that case, if F will be 0 into B plus C bar. थोड़ा कैलकुलेशन कर लीजिए क्योंकि हम तो ब्लैक बोर्ड में ही पढ़ाना ज्यादा पसंद करते हैं. यहाँ पे थोड़ा प्रॉब्लम है ऑनलाइन, बट you can calculate it. So F equal to AB plus C bar. In case of M0, M0 means line M is stuck at 0, A will be 0. उसका इफेक्ट आउटपुट में क्या आएगा? जो आपका जो AND गेट का आउटपुट, that will be always 0. Output of gate number 1 will be 0 in case of M0. Okay, so circuit output F will be simply C bar. तो देखिए ये जो टेबल है राइट हैंड साइड में जो टेबल है उसमें FM0 उसका कॉरस्पॉन्डिंग आउटपुट लिखा गया है. एंड दैट आउटपुट इज नथिंग बट जो C का कॉलम है, इनपुट्स में जो C का कॉलम है उसको जस्ट कॉम्प्लीमेंट करके लिख दीजिए. If C is 0, M0 is 1. If C is 1, FM0 is 0. So in this way the second column, सेकंड क्या मतलब इनपुट्स को छोड़ के FM0 का जो कॉरस्पॉन्डिंग कॉलम है उसको लिखा गया है. ठीक है. सिमिलरली FN0, FN0 means if line number N is at stuck at 0. That means in this case also line number 1, get output of gate number 1 will be 0 and output of the circuit will be C bar only. So FM0, the column corresponding to FM0 and column corresponding to FN0, they are identical. ठीक है. Both the columns are identical. Similarly, if line number P is at stuck at 0, then also output will be C bar only. So here you see that FM0, FN0 and FP0, the columns corresponding to FM0, FN0 and FP0, they are same, identical. It means that these three faults are equivalent faults. They have the same effect on the circuit output. So these faults are indistinguishable faults. Which faults are in this example? You see that M0, M0, N0 and P0. These three faults are indistinguishable. Indistinguishable means that by observing the output, we cannot distinguish whether it is due to M0 or N0 or P0. And we call these faults as equivalent faults. Okay. Now, Another thing is that the circuit may have undetectable faults also. There may be some faults which are not detectable. Actually, undetectable faults can occur in redundant circuits. Actually, redundant means that suppose it is not uh, not implemented in its minimal form. So due to redundancy, what happens? The output may not depend on some logic on some lines or some input, because there is redundancy in the circuit. So those circuits will be undetectable. Undetectable means that even if you cut that line, or even if you short that line to suppose logic 0, the output will remain unaffected. So whether that line is shorted or open or tied to power supply, or it has been connected to ground, it is not going to affect the output of the circuit. So in that case, you will get undetectable faults. But in minimal realization, if there is no redundancy in the circuit, then all the faults are detectable. Because here, the logic on any line, if that logic is changed, the output will also change. So that fault is noticeable. Okay, so undetectable faults occur in redundant logic circuits. And if the circuit is realized using them in its minimal form, there is no redundancy in the circuit, then all the faults will be detectable. Here actually we have realized the circuit in its minimal form. Further reduction is not possible. So here the faults will be detectable. In case of undetectable fault, what happens? The fault-free output will be same as faulty output. In case of undetectable fault, fault-free output will be same as faulty output. In this example, if you see that the fault-free output is not exactly the same of any जितना भी हम लोगों ने कॉलम से लिखा faulty outputs in present of false, उसका कॉलम के साथ आप देखें, you can just compare. For example, let us compare our fault-free output F with FM0 for all possible input combinations. So you see that they are differing. कहाँ पे differ कर रहा है? 1 1 1. You see that if input combination is 1 1 1, then fault-free output is 1, or is faulty output, the fault due to M0, that is FM0, or FM0, that is 0. And other input combinations, they are same. Here, the inputs which will apply, that is known as test. So here, जो input में हम apply कर रहे 0 0 0 0 0 1, so there's 8 combinations, so they are test. In fact, 0 0 0 we call it test 0, just we take the decimal value. Instead of telling that 0 0 0, we simply call it test 0, test number 0. 0 0 1 is test number 1. Similarly, test number 6 is 1 1 0. Okay, so instead of telling the exact input combinations, we simply use decimal number and we call it test number. For example, if we call it perform test number 4, it means that you have to apply 1 0 0 at the circuit input. That's all. So जो राइट हैंड साइड में जो टेबल है, वो टेबल में क्या है कि फॉल्ट फ्री आउटपुट, एंड we have listed all possible outputs in presence of faults. And here we are assuming single faults. We are actually not considering that circuit is subjected to multiple faults simultaneously. What does it mean? It means that if there is M0, so no other faults are present, only one. Of course, it is assumption, single fault. You can perform multiple tests. We can also design the test for multiple faults also. But what happens that it has been seen that if you even consider single faults, that is okay. Okay means that it also give you, in practice, what happens that the probability of multiple, statistically, the probability of multiple failures is much less as compared to the probability of occurrence of single faults. The probability of occurrence of multiple faults, that is quite unlikely. The probability of occurrence of single faults are more. That is one fact. Second fact is that if you perform test for single faults, they automatically cover many tests for multiple faults also. So it is quite reasonable and practical to consider multiple single fault. What we are discussing, it is practically it is not impractical. In fact, practically यही ज़्यादा किया जाता है, क्योंकि automatically it also guarantees the absence of many multiple faults, and the probability, the chance multiple faults का काफी कम है as compared to single faults. So that's why this is also it works well. तो ये समझ में आ रहा है. सो इन दिस कंटेस्ट हम लोगों ने कुछ डेफिनेशन हमने डिस्कस किया कि व्हाट इज टेस्ट. टेस्ट मतलब जो इनपुट कॉम्बिनेशन वही है. वी डिस्कस इक्विवेलेंट फॉल्ट्स. इक्विवेलेंट फॉल्ट मींस FM0. Here you see that FM0, FN0 and FP0. है ना, M0, N0, P0, these three faults are equivalent. Similarly, you see that P1 and Q1, these two faults are also equivalent. FP1 and FQ1. P1 means FP1 means the output of the circuit when line number P is at 1. So obviously you see that if P is at 1, that is the input of the OR gate. P is 1. If you put P is 1, the output will always be 1. है ना, so वही सारे कॉलम 1 है. और P1 and Q1, these two faults are equivalent faults, isn't it? Similarly, you see, हाँ बस इसमें वही है, M0, N0, P0, these three faults are equivalent, and P1 and Q1, these two faults are equivalent. तो equivalent faults और indistinguishable faults ये हमने बताया. और detectable for undetectable faults. Detectable faults means here all faults are detectable because जो भी कॉलम है, आप FM0, FMN0, FQ0 और जितना भी है, अब देखिए कोई भी कॉलम जो फॉल्ट फ्री आउटपुट F इज द फॉल्ट फ्री आउटपुट, उसके साथ मैच नहीं कर रहा है, so that fault is detectable. Now suppose whether line number M is target 0 or not. For that, which test we have to apply? Suppose, consider the situation that the circuit, it is known that line number M is target 0. Okay. So which test, what input combination we have to apply? You see that if we apply 0, 0, 0, so fault free output is 1, and faulty output, that is also 1. So 0, 0 is of no use because 0, 0, 0, this input combination cannot detect M0. The reason is that it does not matter whether line M is line M is at target 0 or not. The output will be 1 only. Fault free output and faulty output, they are identical. So which test we have to apply? For 0, 0, 1, here also you see that fault free output and faulty output same. है ना? And if you see F and just go through the two columns F and FM0, you see that these and their entries, they differ only for 1, 1, 1. है ना? So the test which is required to detect M0, what you have to do? We have to perform exclusive OR operation, F exclusive OR FM0. After this exclusive OR operation, जहां पे आपका output is 1 after exclusive OR, है ना, that will give you the test which can be used to detect that particular fault. You just perform exclusive OR operation with F and F exclusive OR FM0. है ना. So you see that for test number 111, when inputs are 111, है ना, there you will get 1, and for all other inputs this exclusive operation will give you 0, है ना. So test number 7 is required to detect M0. Okay, so from this table we will construct fault table जो बाद में है. Fault table, ये देखिए fault table. Here what we have done, this table is directly derived from the previous table, this table. Here what we have done, inputs ABC, these are the test and possible faults. Here we have combined the equivalent faults because M0, N0, P0, they are equivalent faults. So you can combine them, or you can consider any one out of this, one representative fault. Okay. Similarly, P1, Q1, they are equivalent fault. तो उसके लिए हम लोगों ने combine कर दिया. So effectively now, actually here is these three and other faults are Q0, M1, N1. ये लिखा गया है. Now this table is obtained simply by taking exclusive OR of F, मतलब fault free output और faulty output. ये दोनों का exclusive OR लेके इसको लिखा गया. जहाँ पे 1 है वही एंट्री लिखा है, बाकी 0 को नहीं शो किया गया है ना. So here I am showing you. You just take F exclusive OR FM0. And you see that for except for test number 111, test number 7, all other entries will be 0. वो यहाँ पे लिखा गया टेबल में, यहाँ पे देखिए. So 111 here, ठीक है. Similarly, the column corresponding to Q0, it is obtained by performing F exclusive or FQ0. जो previous table था, you just perform F exclusive or FQ0, and you will see that there are 3 entries corresponding to test number 000, 010, and 100. You can check it. You just see column corresponding to F and FQ0, and you see that where they are differing. देखिए 000 में डिफर कर रहा है तो वहां पर 1 लिखा गया है. 001 में सेम है, फॉल्टी आउटपुट एंड फॉल्टी आउटपुट सेम, तो उसको नहीं, वो 0 है ना. इस तरह से आप देखिए यहाँ पे एंट्री जहां पे डिफर करे वहां पे 1 है. So this table is, in this way you can perform this, you can construct this table, and this table is known as fault table. Okay. Now what does it mean, this fault table? इसका मीनिंग ये है, कॉलम वाइज देखें, इफ देयर इज जिसे आपका M0, N0, P0 पहला है ना, you see that there is 1, एक 1 है. It means that these faults can be detected by using test number 7, that is 111. ठीक है. In fact, that this is the only test using which you can detect these faults. अगर कॉलम में सिंगल एंट्री है, कॉलम वाइज देखिए सिंगल एंट्री है, फॉर एग्जांपल द कॉलम corresponding to M1 है ना, you have only one test 011. That means that this is the only test by using which you can detect M1. So N1, you see that 101, this is the only test. तो जहां पे देखिए एक कॉलम अगर सिंगल है तो उसको एनसर्कल किए, इसका एक पर्पस है, एनसर्कल किया हुआ, because those ultimately. Hello.
Yes, sir.
Hello.
Yes, sir.
Okay.
So you may continue, sir.
Okay. So here you see from this table what we wish to determine. We wish to determine minimal complete test set. So test set, complete test set means, first I will discuss what is test set. Test set is simply set of some test. Test क्या है? Input combination, inputs, decimal form में लिखा गया है. So set of test, that is test set. Complete test set means the test set which can detect all the faults under consideration. ठीक है. So in this case we are considering 8 faults, तो 8 faults detect हो जाएगा. That is the complete test set. So complete test set is one possible complete test set will be that truth table method. You consider all the input combination. So complete test set will contain eight tests. 0, 1, 2, 3, 4, 5, 6, 7. Suppose हम सारे टेस्ट को लेने चाहते हैं. So that is complete test set. Complete test set means using that test set, you will be able to detect all the faults under consideration. Minimal complete test set means that we will not consider 2 to the power under 8 tests. It contains a minimum number of tests. So minimum number. What is the minimum number of tests? What is the minimum set of tests using which we can detect all the faults under consideration? है ना? तो मिनिमल कंप्लीट टेस्ट सेट हम जो टेबल का नीचे लिखा वो हम निकालना चाहते हैं. तो फर्स्ट यू सी दैट बिकॉज फॉर डिटेक्टिंग M1 वी नीड टेस्ट नंबर 3 बिकॉज दैट इज द ओनली टेस्ट टिक लगा हुआ लेफ्ट साइड में 3 टेस्ट जो है सर्कल करके दे मस्ट बी द मेंबर ऑफ मिनिमल कंप्लीट टेस्ट सेट. Reason is that to detect M1 we need test number 3 because no other test can detect. क्योंकि वहीं पे डिफर कर रहा था. When you taking exclusive OR of F and FM1, so those entries differ only for ABC जहाँ पे 0, 1, 1 है. So we must have to take that, है ना? Otherwise we will not be able to detect M1. Similarly, for N1 we must consider test number 5 101, that is ABC 101, because that is the only test using which we can detect N1. So that test must be the member of minimal complete test set, because if we do not consider that test, so we will not be able to detect N1. Okay. Similarly M0 का केस में आपको टेस्ट नंबर 7 को लेना है. तो ये जो 3, 5, 7 they are essential test. Essential test means they are essential for detecting all the faults in the circuit. They are essential, but they are not complete. Still, they may not be complete, है ना? तो अब देखिए, consider इस टेबल का देखिए 011 उस जो है टेस्ट नंबर ABC 011 है ना, जहां पे पहला टिक लगा उसका रो को देखिए. रो in that row we have 2 ones. एक M1 कॉलम का नीचे है, एक वो जो P1 Q1 लिखा है उसमें उसका नीचे एक 1 लिखा हुआ है ना. So it means that test number 3 not only detects M1, it also detects P1 and Q1. ठीक है. अगर आप रो वाइज पढ़ेंगे टेबल को तो उसका मीनिंग ये है कि टेस्ट नंबर, क्योंकि जहां पे 1 है हम लोग एक्सक्लूसिव ऑल लेके उसको किया है. So P1 Q1 ये जो fault है they can also be determined using test number 3 only. So for the P1 and Q1 हमको अलग से कोई टेस्ट और लेने का जरूरत नहीं है. If you are considering test number 3 in the minimal complete test set, so P1 Q1 will automatically, that fault will also be detected by test number 3. Okay. Now only remains we have to detect Q0, because टेस्ट नंबर 3, 5, 7 they cannot detect Q0 fault. आप क्योंकि Q0 fault में देखिए वो है ही नहीं. Q0 fault can be detected by test number 0, that is input is 000, 010 means test number 2, or test number 4 means 100. So Q0 fault can be detected. For detecting Q0 fault you can use test number 0 or 2 or 4. Okay. So in this example, if we take minimal complete test set will be 3, 5, 7, they are the essential test, they are the member of EA, and we have to consider one more test. You can choose 0 or 2 or 4. You have to choose one test out of 2, 0, 2 and 4. Then you see that all the faults can be detected. So minimal complete test set consists of only 4 tests. For example, we can take 3, 5, 7, 0, or we can take 3, 5, 7, 2, or we can take 3, 5, 7, 4. Okay. So in truth table method, you are supposed to test the operation of circuit for 8 possible input combinations. But here you see that to detect staggered faults, these faults, you need not rigorously test the fault table, truth table. You just check whether the circuit is operating correctly for these 4 input combinations or not. C, that is you apply 0, 1, 1, 5, apply at the input 1, 0, 1, 7, 1, 1, 1, and 0, 0, 0, 0. And if the circuit produces correct output for these 4 possible input combinations, that means that circuit is okay. It is free of these kind of faults. So you see that we have reduced the testing time by 50%. 8 input combination के लिए टेस्ट करने की जरूरत नहीं है ना? आप 4 input combination चेक कर लीजिए, and if the circuit produces correct output, बाकी जो faults है वो automatic covered है इसी में से. So testing time will be less. In fact, for this example, it will 50% आपका testing time. So cost of testing will be reduced to 50%, है ना? So this is just a basic concept of fault table method. Now, there's some drawbacks of testing table. Here also you see that if number of inputs are large, तो यहाँ पर भी देखिए जो competition काफी होगा, और intermediate lines, number of wires, है ना? So the fault table, the size of this table will be more. So in that case, actually there are some other some observations. There are some what we can say, some methods for reducing the test fault table further, है ना? वो actually आगे का पढ़ने का है, वो हमने यहाँ पे discuss नहीं कर रहा हूँ. I have taken only simple example just to discuss the basic concept behind fault table. Or in case of large scale, you can take help of computer. Instead of doing it manually, you can use some algorithm for this, है ना? But technique is simple. It is not difficult to understand or to construct the fault table. But still, computation of the fault table, it will be actually more. If it manually impossible, even with the help of computer, उसका computation ज़्यादा होगा. If number of inputs or number of intermediate lines are large. Okay, so then we will go for the second method, path sensitizing method. Now here in fault table method, we focused on one single wire, whether it is at stack at 0 or stack at 1 or not. And then we have we are concentrating on single fault. जैसे Q0 तो Q0 में ही concentrate हम लोगों ने किया कि Q0 को detect करने के लिए क्या क्या हमको test चाहिए. And we have determined it by taking exclusive or the fault free output with FQ0, the faulty output, है ना? Faulty output. And then we constructed this. Now, in case of path sensitizing method, instead of concentrating on one single fault, single wire, we will concentrate on one single line from input to output. So, in that case, computation will be very less, and it will be computationally attractive. So, next we'll discuss the path sensitizing method. The circuit is same, but here actually the input को हमने change कर दिया so that you can calculate it easily. वहाँ पे क्या था, ABC बात है, यहाँ पे input में हमने X, Y, Z ले intention लिया to make computation आप manually कर सकते हैं, मतलब mind में कर सकते हैं इसलिए. So first we'll designate the wires. We have designated the wires A, B, D, है ना? नीचे वाला C, output line E. Output जो वायर है उसको भी consider किया यहाँ पर. Okay. So from input to output you see that जिसे input X है वहाँ से output एक path है. The path ADE. Similarly, in this, instead of considering 5 lines, what we'll consider the paths from input to output. And there are three paths from input to output. Starting from X to F, the path is ADE. Starting from Y to output, the path is BDE. And starting from Z to F, the path is CE. Okay. Now, what we will do, फॉर एग्जाम्पल ये जो टेबल है उसका फर्स्ट एंट्री को देखिए, पाथ इज एडी, वी हैव कंस्ट्रक्टेड वन टेबल, उसमें क्या है, पाथ इनपुट, इनपुट वेरिएबल्स रिक्वायर्ड टू सेंसिटाइज द पाथ, इसका मीनिंग हम बताएंगे, फिर टेस्ट नंबर फॉल्ट्स डिटेक्टेड. सो लेट अस कंसीडर द पाथ एडीई. ओके, एंड वी हैव अप्लाइड x equal to 0, सपोज इनपुट x equal to 0. Now sensitize the path means ADE, मान लीजिए कि ये जो फॉल्ट है, if we apply x equal to 0, then we can detect whether line A is stuck at 1 or not. See, if line A is stuck at 0, that means that where a line A, it is always at logic 0. To detect that, हम लोग को x में 1, अच्छा मैं उल्टा करके बोल रहा हूँ, हाँ, suppose we wish to detect whether line A is stuck at 1 or not. 1 को पहले कंसीडर करते हैं, whether the line A is stuck at 1 or not, तो x में क्या अप्लाई करना पड़ेगा, जो फॉल्ट हम डिटेक्ट उसके जस्ट ऑपोजिट लॉजिकली रिवर्स लॉजिक वहां पे अप्लाई करना पड़ेगा. इफ वी यूज टू डिटेक्ट line A is at stuck at 1 or not, that is A1, so we have to apply x equal to 0, because if you apply suppose x equal to 1, तो लाइन है तो फॉल्ट के वजह से 1 में है ही है, आप 1 अप्लाई करिए तो डिटेक्टेबल नहीं होगा आपका, क्योंकि वो ऑलरेडी 1 में ड्यू टू फॉल्ट. तो वहां पे क्या है कि 0 अप्लाई करके आप हमको देखना है कि 0 उसमें पास हो रहा है कि नहीं लाइन के थ्रू. एक एंड में एक लाइन मान लीजिए कि 1 के साथ लॉजिक 1 के साथ स्टक एट लॉजिक 1, एक लाइन, कोई भी एक लाइन को मान लीजिए कि इट हैज बीन कनेक्टेड ड्यू टू फॉल्ट, इट हैज बीन कनेक्टेड टू सपोज VCC. नाउ टू डिटेक्ट दैट फॉल्ट, एक एंड में हमको 0 अप्लाई करेंगे और दूसरा एंड में अगर 0 मिल रहा है तो that is okay, there is no stuck at 1 fault. And if you apply 1, तो 1 तो ड्यू टू फॉल्ट भी 1 मिलेगा, तो 1 is not required. We have to apply just जो फॉल्ट हम डिटेक्ट करना चाहते हैं उसका जस्ट उल्टा रिवर्स लॉजिक हमको यूज करना है. So what I mean to say that if line A is stuck at 1, to detect stuck at 1 fault at line A, x should be 0. तो वो पहला x equal to 0 लिखा गया है, ठीक है. Now due to stuck at 1 fault, what will happen, the x equal to 0, that correct 0 will be incorrect 1 at line A due to the fault, if there is fault. Now this fault should propagate from input to output. तो उसके लिए हमको y और z को assign करना है. We will assign in such a manner that fault should propagate from input to output. Now पहला गेट क्या है, एंड गेट. नाउ if we assign y equal to 0, तो एंड गेट में क्या होता है कि एक इनपुट 0 तो ऑलवेज 0. So if we, तो fault will not be propagated. So to propagate that fault, what you have to do, we have to apply y equal to 1, because if we make y equal to 1 तो एंड गेट है, तो any fault on line A, that fault का इफेक्ट आउटपुट में नोटिसेबल होगा, आउटपुट ऑफ लॉजिक 1. Similarly, in case of OR gate, the other input should be 0. In general, what happens, the fault will be propagated from input to output. So if in the path, if you encounter with AND gate or NAND gate, तो उसका जो अदर इनपुट है, अदर उस पाथ को छोड़ के उसमें हमको आपको असाइन करना है 1. And in the path, if you encounter with OR gate or NOR gate, तो अदर इनपुट को 0 असाइन करना पड़ेगा. then only the fault, the effect of that fault will be visible at the gate output. है ना, ये जो अदर वेरिएबल्स अदर देन इनपुट, जो इनपुट इसको छोड़ के जो अदर वेरिएबल्स will assign those variables in such a manner that the fault should propagate along the line. और ये जो हम assign करें उसी को कहते हैं sensitize the path. Sensitize the path means we are assigning other variables in such a manner that the fault will be propagated along the path. The purpose is that fault को हमको propagate करवाना है from input to output. तो उस हिसाब से हम other variables, other input variables को choose करेंगे. I think now you can understand the table. So first path हम लोगों ने लिया है ADE, input x equal to 0. To sensitize the path other variable input variable, that is yz, y को हमको 1 करना पड़ेगा क्योंकि एंड गेट है 1, देन ओनली जो बताया कि आउटपुट जो A1 का जो इफेक्ट है वो आउटपुट ऑफ 1 गेट 1 में विजिबल होगा. नेक्स्ट DE, यहाँ पे देखिए DE, यहाँ पे क्या है और गेट, दिस पार्ट क्या है गेट 2 D2E. तो अगर D में कोई फॉल्ट है वो E में प्रोपागेट होगा अगर Z 0 हो, क्योंकि और गेट है. अगर Z को हम 1 कर दे तो क्या होगा कि वो तो और गेट है, और गेट में एक इनपुट 1 है तो आउटपुट ऑलवेज 1, तो उसका फॉल्ट का इफेक्ट आउटपुट में विजिबल नहीं होगा. तो Z इक्वल टू 0 करना है ना. तो ये थोड़ा लॉजिक लगा कि अगर आप देखें, मतलब वी हैव टू असाइन अदर वेरिएबल्स इन सच ए मैनर दैट द पाथ शुड बी सेंसिटाइज्ड. सेंसिटाइज्ड मींस द फॉल्ट शुड बी प्रोपागेटेड फ्रॉम इनपुट टू आउटपुट. सो उस तरह से हम लोगों ने इसको किया. तो y इक्वल टू 1, z इक्वल टू 0. सो टेस्ट नंबर क्या है? टेस्ट नंबर यहाँ पे एक्स वाई जेड, एक्स को हम मोस्ट सिग्निफिकेंट पोजीशन में रखे एक्स वाई जेड. तो 0 1 0 इन डेसिमल 0 1 0 इज 2. सो टेस्ट नंबर 2, तो 2 लिखा गया. एंड व्हिच फॉल्ट विल बी डिटेक्ट, द फॉल्ट्स डिटेक्टेड बाय दिस टेस्ट नंबर 2 यू कैन डिटेक्ट A1 D1 एंड E1. तो 3 फॉल्ट आपका डिटेक्ट हो जाएगा A1 D1 E1 यूजिंग टेस्ट नंबर 2 ओनली. ठीक है. Similar way for x equal to, we are suppose same path we are applying x equal to 1. तो input variable is required to sensitize the path, तो same रहेगा y equal to 1 z equal to 0. Now test number क्या होगा 6 1 1 0, x equal to 1 x y z 1 1 0, तो 1 1 0 in decimal 6. And in this case because x 1 आपने apply किया, so you will be able to start at 0 faults, that is A0 D0 and E0. ठीक है. तो सिमिलर वे BDE नेक्स्ट पाथ BDE, इसको हम कंसीडर कर रहे हैं. तो इनपुट वेरिएबल y को 0 अप्लाई किया गया. नाउ द इफेक्ट ऑफ दिस विल बी प्रोपागेटेड अलोंग द पाथ. तो x जो एन गेट है, अदर इनपुट इज x, सो x मस्ट बी 1. देखिए उस रो में तो x इक्वल टू 1 लिखा गया है. सेम लॉजिक में z को 0 किया गया, क्योंकि और गेट है तो द आउटपुट D2E, the fault will be propagated from D2E if Z equal to 0. So this will give you test number x y z उस ऑर्डर में लेना है. x 1 है 1 y 0 z 0, तो 1 0 0, so 1 0 0 is 4, तो 4 लिखा गया है. सिमिलर वे y इक्वल टू 1 के लिए सेम है. C का एक एंट्री देखते हैं. C पाथ, कंसीडर पाथ C z इक्वल टू 0. ठीक है. यहाँ पे देखिए z इक्वल टू 0. So you will be able to detect C1 whether line C has target 1 or not. ठीक है. So the fault will be propagated from C to E if D equal to 0. क्योंकि और गेट है तो D को 0 होना है. अब देखिए यहाँ पे हम बैक प्रोपेगेशन लगा रहे हैं. D को 0 होना है. D 0 कब होगा? The output of NAND gate, output of gate number 1 AND gate, that will be 0. और 3 कॉम्बिनेशन के लिए 0 हो सकता है. एक्स वाई दोनों, मतलब 1 1 नहीं होना चाहिए. 0 0 हो सकता है, 0 1 और 1 0, वो लिखा गया है. तो अदर इनपुट वेरिएबल्स रिक्वायर्ड टू सेंसिटाइज द पाथ. तो यहाँ पे x इक्वल टू 0 y इक्वल टू 0 और 0 1 1 0, बस 1 1 नहीं होना चाहिए. ठीक है ना. एंड इट विल गिव यू टेस्ट नंबर. देखिए फॉर 0 0 0 उसी x y z इसी ऑर्डर में हमको टेस्ट को लिखना है. तो 0 0 0 दैट इज टेस्ट नंबर 0. उसके बाद क्या है 010 दैट इज टेस्ट नंबर 2, 100 दैट इज टेस्ट नंबर 4, है ना. सो वी कैन यूज टेस्ट नंबर 0 और 2 और 4 टू डिटेक्ट C1 E1. ठीक है, उसी का रिवर्स कर देंगे Z इक्वल टू 1, और सेंसिटाइज करने के लिए XY वेरिएबल और नीचे लिखा गया है ना. तो इट विल बी 1, 3 और 5 एंड यू कैन डिटेक्ट C0 एंड E0. सो फॉल्स डिटेक्टर्स यहाँ पे आप देखिए जितना भी हमारा फॉल्ट है, मतलब 10 पॉसिबल फॉल्ट्स, बिकॉज यू कंसिडर 5 लाइन्स ABCDE. Each line can be at stuck at 0 or stuck at 1. So we have देखिए सारे फॉल्स को हम लोगों ने यहाँ पे फॉल्स डिटेक्टर्स कॉलम में ऑल आर प्रेजेंट ना. यहाँ पर भी इफ देयर इज सिंगल टेस्ट तो एसेंशियल टेस्ट उसको लेना ही लेना है. सो 2, 4 एंड 6 जो आंसर कर ले वो मास्ट है, 2, 4, 6 लेना है. तो 2, 4, 6 यू सी द टेस्ट नंबर 2 जो पहले लिखा गया है ऊपर BD लाइन में, the test number 2 will also detect C0 E0, because यहाँ पे देखिए C लाइन पे भी 0 और 2 और 4 लिखा गया है, because 2 ऑलरेडी हम लोगों ने कंसीडर किया एनएसएस टेस्ट में, तो C1 E1 उसमें इंक्लूड हो गया. और क्या है BD लाइन में Y इक्वल टू 1 उसमें 6 वो भी हो गया. तो ओनली थिंग C0 E0, 2, 4, 6 these essential tests can detect all the faults except C0 and E0, है ना. So minimal complete test set will be 2, 4, 6 तो रहेगा essential test, and we have to choose one test from test number 1 or test number 3 or test number 5. So minimal complete test set consists of 4 tests, 2, 4, 6, and you have to choose only one test out of these 3, 1, 3 or 5. Actually जो पहले हम लोगों ने डिस्कस किया फॉल्ट टेबल मेथड वही है, बट एक ही डिफरेंस है, वो अगर सी बार है ना, अगर उसको लॉजिक को बदल देंगे तो इसके साथ मैच कर जाएगा. बिकॉज हियर वी हैव कंसीडर्ड XYZ, वहां पे C बार था, सी बार के कारण डिफरेंस आया है. अदरवाइज वहां पर अगर सी बार को आप Z मान लीजिए तो सेम आएगा. जो टेस्ट है उसको लिखिए बाइनरी में एंड एस्यूम A को X मानिए, B को Y मानिए और सी बार को Z मानिए, सी बार को Z मानिए, and if you write that it will match with this, है ना. So this is the path sensitivity method. Advantage is that it is computationally less complex as compared to fault table method. Drawback is that sometimes it is not possible to sensitize all the paths in the circuit, especially if there is some feedback connection or fan out lines. Fan out means suppose the gate output is connected to more than two or more gates. So in those situations sometimes it is not possible to sensitize the path, so those circuits cannot be analyzed. But if the fan out lines मान लीजिए कि 1 है, मतलब एक से ज्यादा गेट को ड्राइव नहीं कर रहा है, और that is those kind of circuits are known as tree like circuit. So for tree like circuit it works well. बट जहाँ पे आपका सपोज गेट आउटपुट, जब गेट नंबर 1 यहाँ पे एक ही गेट के साथ कनेक्टेड है, गेट नंबर 2, सपोज इफ इट इज कनेक्टेड टू मल्टीपल गेट्स, और इफ देयर इज सम व्हाट इज कॉल्ड फीडबैक टाइप ऑफ कनेक्शन, सो इन दोस सिचुएशंस इट इज नॉट always possible to sensitize all the paths in the circuit. So if you cannot sensitize, then path sensitize method will fail. Otherwise for tree like network, tree like connection, this method is beneficial as compared to fault table method. Okay, next we will go for Boolean difference method. So before that I will just define what is Boolean difference. We will discuss the definition of Boolean difference. Here f is a switching function. Suppose fx, it is a function of n variables, x1, x2, x3, है ना. ith variable is denoted by xi. Then df dxi, that is the Boolean difference of the Boolean fx with respect to one of its variable, ith variable of x. So df dxi, है ना, d dxi of fx, that is actually exclusive or of these two. अब देखिए लिखा है सेकंड लाइन देखिए, एफ ऑफ x1 तो ए फंक्शन है एक्सक्लूसिव और ओनली xi वेरिएबल जिसके रिस्पेक्ट में आप बुलियन डिफरेंस निकालना चाहते हैं दैट विल बी कॉम्प्लीमेंटेड एफ ऑफ x1 अप टू लिखा गया xi बार xn नाउ दैट इज इक्वल टू जो नीचे इक्वल करके जो लिखा गया एफ ऑफ x1 xi माइनस 1 0 xi प्लस 1 अप टू xn एक्सक्लूसिव और वही जो xi का प्लेस में 1 लिखा गया है because x1 x2 x3 they can assume only two values 0 or 1 so in the previous expression if you put xi equal to 1 then also it will be equal to this second one if you put xi equal to 0 then also है ना so this is the definition of Boolean difference so Boolean difference means that this will be if fx it depends on xi then the value of this difference will be 1 but if fx is independent of xi मतलब उसके ऊपर कोई डिपेंड ही नहीं कर रहा है then the value of this will be 0 है ना now उसके बाद देखिए small example how to find out Boolean difference we have taken one example suppose function is x1 x2 plus x3 तो जो definition में xi है ना we wish to find out Boolean difference of this function with respect to x1 ठीक है so what we will do first we जो expression है उसमें x1 का प्लेस में 0 लिखिए 0 into x2 plus x3 एक्सक्लूसिव और उसी प्लेस में 1 लिखिए 1 into x2 plus x3 फिर आफ्टर सिंप्लीफिकेशन यू विल गेट Boolean difference x2 x3 ठीक है and it has certain properties for example that d dxi of fx will be same as d dxi of fx bar इसके फिजिकल इंटरप्रिटेशन ये है कि if fx is independent of xi then complement of fx will also be independent of xi if fx depends on xi then complement of fx will also depend on xi और एनालिटिकली आप उसको ये कर सकते हैं है ना मतलब ये जो डेफिनेशन है इसका प्रूफ आप कर सकते हैं सेकंड प्रॉपर्टी उसका नीचे लास्ट में लिखा गया है d dxi of fx is same as d dxi bar of fx मतलब ये हुआ कि if fx depends on xi then fx will also depend on xi bar है ना so and from definition you can prove these things this proof is very not easy basically क्या है कि a exclusive of b is same as a bar exclusive of b bar है ना using this actually आपका प्रूफ हो जाएगा a exclusive of b is equal to a bar exclusive of b bar इस टाइप का एक प्रॉपर्टी लगेगा प्रूफ हो जाएगा so this is Boolean difference और next we'll see how to detect faults how this Boolean difference helps for detecting faults okay तो fault detection using Boolean difference यहाँ पे जो टेस्ट हम लोग वहां पे क्या करते थे एक्सक्लूसिव वाल ले रहे थे और वो जो फॉल्ट टेबल मेथड पाथ सेंसिटाइजिंग मेथड हम लोगों ने डिस्कस किया यहाँ पे क्या है कि सेट ऑफ टेस्ट टू डिटरमिन द सेट ऑफ टेस्ट फॉर डिटेक्टिंग स्टैकेड जीरो फॉल्ट व्हाट यू हैव टू डू पहले कि फॉल्ट को डिटेक्टेबल होना पड़ेगा इफ fx डिपेंड्स ऑन xi इसका मतलब ये है इफ d dxi of fx is 1 it means that the fault is detectable if d dxi of fx is 0 it means that fx is independent of xi and fault is not detectable because output में कोई effect ही नहीं है so ये जो second term d dxi fx it must be 1 to detect the fault और क्या है क्योंकि हम स्टैकेड जीरो फॉल्ट डिटरमिन करना चाहते हैं डिटेक्ट करना चाहते हैं टू डिटेक्ट स्टैकेड जीरो फॉल्ट तो लॉजिक एट xi इट मस्ट बी 1 वही लॉजिकली ऑपोजिट बोला रिवर्स तो स्टैटिक जीरो फॉल्ट का हमको 1 देना पड़ेगा सो यू कैन डिटरमिन द सेट ऑफ टेस्ट फॉर डिटेक्टिंग स्टैकेड जीरो फॉल्ट एट xi तो दो कंडीशन देखिए xi मस्ट बी 1 एंड आउटपुट शुड डिपेंड ऑन xi so वही लिखा गया है if is a condition xi and d dxi fx equal to 1 इसको हम सॉल्व करेंगे और जो जो इनपुट कॉम्बिनेशन के लिए आफ्टर सॉल्विंग दिस वी कैन फाइंड आउट द टेस्ट. Okay. Similarly, to detect stack at one faults, what you have to do? क्योंकि stack at one fault हम detect करना है, तो we have to apply 0 at xi. That means xi bar is true. So if xi bar is true and output depends on that variable. If fx d dxi of fx, this is 1. If both are 1, है ना? That is xi bar dot means and d dxi of fx equal to 1. है ना? It will give you by solving this, you will get the test which will be required to detect stack at one fault on si xi line. Okay. So हम लोग सेम एग्जांपल हम ले रहे हैं, बट यहाँ पे सपोज एक सिंगल एक फॉल्ट डिस्कस करते हैं. Suppose you used to detect whether line number A is stacked at 0 or not. So what you have to do? We have to solve the equation stacked at 0 fault. So you have to solve x1 dot df dx1. So f हम जानते हैं f क्या है, x1 x2 plus x3. Output expression is x1 x2 plus x3. So first you find out df dx1. In fact हम लोगों ने वही फंक्शन लिया था. देखिए उसी फंक्शन को पहले डिस्कस किया. यहाँ पे इस स्लाइड में fx equal to x1 x2 plus x3, तो we have seen that it is simply x2 x3 बार, है ना. So x2 x3 बार, तो उसको हमको चाहिए. तो यहाँ पे देखिए नेक्स्ट स्लाइड में लिखे टू डिटेक्ट स्टैक एट 0 फॉल्ट एट लाइन ए x1 we have to solve x1 df dx1 equal to 1. इसको सॉल्व करना है. तो x1 it implies that x1 on df dx1 क्या होगा, x2 plus x2 x3 बार. You see that for which input combination this will be satisfied. The input will be, we have to take x1 equal to 1, x2 equal to 1 and x3 equal to 0. That is 1 1 0. And that is correspond to test number 6. In fact, the test number 6 आपका उसमें भी आया था, fault table method and path sensitizing method. You will see that A0 fault को डिटेक्ट करने के 6 है ना, वो consistent है. देखिए हम दिखा रहे हैं यहाँ पे. देखिए A0 फॉल्ट को देखिए, जो सेकंड रो टेबल का राइट में जो टेबल है A0 टेस्ट नंबर 6, वही चीज यहाँ से भी आ रहा है, टेस्ट नंबर 6. ठीक है. Similar manner to detect stack at one fault, what you have to do, you have to solve x1 bar df dx1 equal to 1. तो एक यहाँ पे x1 बार और df dx1 बार आप हम लोगों ने पहले देखा x2 x3 बार इक्वल टू 1. So this by solving this you will get x1 equal to 0, x2 equal to 1 and x3 equal to 0. So 0 1 0, that is test number 2. वही आपको उसी मेथड से भी टेस्ट नंबर 2 आया था. A1 के लिए देखिए A1 इस टेबल में देखिए A1 फॉल्स डिटेक्ट A1. देखिए पहला फर्स्ट जो एंट्री है ADE पाथ में, यहाँ पे टेस्ट नंबर 2 जो आंसर कर ले, तो टेस्ट नंबर 2 चाहिए. तो सेम रिजल्ट आपको यहाँ पर भी मिल रहा है ना, वो कंसिस्टेंट है सब. Now question is that suppose you want to consider one intermediate line G, and we used to check whether G is at stack at 0 or not. G intermediate line. Now in this case what we will do, we will express the output in terms of G and other input variables. G भी उसमें आए. Then we will find out df, क्योंकि G इसके लिए हमको क्या चाहिए, we have to check whether f depends on G or not. So stack at 0 fault at G, to detect stack at 0 fault at G, you have to solve G dot मतलब and G into हम बोल रहे हैं, वो into नहीं, एक्चुअली लॉजिकल एंड है, G into df dg of f, है ना. So f can be written as G plus x3. Here instead of writing f equal to x1 x2 plus x3, we will write f equal to G plus x3, and from here you can find out ddg of f, and that will give you x3 bar. So that will be used here, है ना. उसको आप कर सकते हैं डेफिनेशन से, वो x3 बार आएगा. तो ये देखिए इस स्लाइड में देखिए, टू डिटेक्ट स्टक एट जीरो फॉल्ट एट लाइन जी वी हैव टू सॉल्व g into dfdg equal to 1. g क्या था? g is the output of the logic gate 1, that is x1 x2, the x1 x2 and dfdg is x3 bar. By solving it you will get 110, decimal value क्या है? 6, so 6. Similarly, to detect stuck at one fault at line g, g bar मतलब x1 x2 का उसका complement आप लेंगे. So in this case you will get this expression will be 1 x2 मतलब x1 bar plus x2 bar into x3. So this is actually x1 bar x3 bar plus x2 bar x3 bar. So x1 bar x3 bar will be 1 for x2 वेरिएबल का आप डोंट केयर ले सकते हैं. तो 0 और 2 ये दो टेस्ट 2 के लिए पहला टर्म जो है वो 1 होगा और सेकंड टर्म जो x2 बार x3 बार वो एक्चुअली x1 को आप डोंट केयर ले लीजिए और x2 इज 0 x3 इज 0. इन दैट केस यू विल गेट 2 और 4. सो ये मिला करके आपको टेस्ट नंबर 3 टेस्ट देगा 0 और 2 और 4. सो यू कैन चूज एनी वन out of these 3 tests to detect stuck at one fault at line G. So in this way, this Boolean difference method works. Okay. So we have discussed, we briefly introduced actually these 3 methods for detecting faults, stuck at faults in combinational circuits. Now, we have not discussed anything about sequential circuit. In case of sequential circuits, what happen? In sequential circuit, we have actually a sequential circuit can be characterized by its state table. It has certain states, some states, and some state transitions. So in that case, actually, we have to suppose one sequential circuit is given to you, and you have to check whether the circuit is operating correctly or not. So for that, in case of sequential circuit, because output depends on previous inputs also, not only present input but previous input. So in this case, first you have to take the circuit to a specified state. Okay, so that is some experiments are there by using which you can state identification problem, state को आप identify कर सकते हैं. And then you have to design some input combination, input sequence, which will take the circuit to all of its states, जितना state है उसमें, and it will take the circuit through all of its transitions. So इस तरह से एक input sequence वहाँ पे design करते हैं, and then applying that input sequence one by one, है ना. So first वहाँ पे दो स्टेप में एक्चुअली काम होता है. पहले in case of sequential circuit, you have to take the circuit to a specified state, and that is the beginning of your experiment. And starting from there, you have to apply one sequence, test sequence, है ना. That sequence will take the circuit through all its states and state transitions, है ना. So in this way actually the fault diagnosis in sequential circuit is done. ये हमें बहुत ही briefly just concept देने के लिए बोला है. इसका discussion में काफी time लगेगा, but ये है. अच्छा, today's discussion we concentrated on only fault detection. Now there is another problem, fault location. Fault detection में means कि whether the circuit has any fault or not, है ना. फॉल्ट डिटेक्शन बस फॉल्ट है, बस फॉल्ट ही है, कहाँ पे वो हमको नहीं पता, फॉल्ट है. तो फॉल्ट को लोकेट करने के लिए अगर कोई फॉल्ट को हम लोकेट कर सके तो और भी इजी है. मान लीजिए कोई एक बोर्ड में फॉल्ट है या कोई चिप में फॉल्ट है, देन क्या करेंगे, हम उसको रिप्लेस कर देंगे. जी यहाँ पे फॉल्ट इस ऐसे काम नहीं कर, चलो इसको हटाओ, दूसरा नया ऐसे लगा दो, करेक्ट ऐसे लगाओ, तो सर्किट काम करना शुरू करेगा. सो दैट इज एक्चुअली फॉल्ट लोकेशन प्रॉब्लम. In this lecture actually we discussed about fault detection, the fault location और आगे का topic है, and their purpose is that how to locate the fault. Fault detection तो है, fault है, but fault कहाँ पे कर किया है ना, that is also required. Then you can repair the fault. So these are the things, and then actually we need fault tolerant design. Fault tolerant design means कि मान लीजिए फॉल्ट है तो सर्किट फिर भी अपने आप उसको करेक्ट कर ले। देयर आर, जैसे मान लीजिए कोई स्पेस में, सैटेलाइट में, कोई स्पेस में जहां पे फिजिकली जाना पॉसिबल नहीं है, वहां पे कोई इलेक्ट्रॉनिक सर्किट है, अब फॉल्ट हो गया तो वो तो नहीं है कि जाके हम ठीक करके आए। तो वहां पे क्या है कि सर्किट को रियलाइज करते फेल्योर टॉलरेंट डिजाइन, द सर्किट विल वर्क इवन इफ देयर इज फॉल्ट, वो मेल फंक्शन नहीं होगा। तो फेल्योर टॉलरेंट डिजाइन, द बेसिक कॉन्सेप्ट इज दैट यू इंट्रोड्यूस रिडंडेंसीज। Normally in most of the design we introduce triple modular redundancy, एक मॉड्यूल के लिए दो मॉड्यूल उसके मतलब बैकअप में स्टैंड बाई दो मॉडल और है। एक मॉडल अगर खराब हो जाते हैं ऑटोमेटिकली वो दो जो रखा हुआ स्पेयर पार्ट्स उसमें वो स्विच, तो इसके लिए भी स्टडी करते हैं कि हाउ टू, कैसे स्विच किया जाए, वो फॉल्टी मॉडल कौन सा है कैसे पता चलेगा, कैसे उसको आइसोलेट किया जाए। सो ये फेल्योर टॉलरेंट डिजाइन में यूज होते हैं। तो बेसिक एक्चुअली फिलोसफी वहां पर ही है कि इंट्रोड्यूस रिडंडेंसीज। तो नॉर्मली रिडंडेंसी 3 को ट्रिपल मॉड्यूलर रिडंडेंसी TMR ये यूज किया जाता है। इवन वहां पे जो लॉजिक गेट होते हैं वो लॉजिक गेट का रिलायबिलिटी बढ़ाने के लिए 4 गेट लगाया जाता है जिसको कहते हैं क्वाड लॉजिक। वो बेसिकली एक ही एंड गेट है बट उसके भी 4, तो इसमें क्या होता है उसका रिलायबिलिटी काफी बढ़ जाता है, तो दैट इज कॉस्टली। और वी नॉर्मली जो स्पेस में जो जाते हैं वहाँ पे जो सर्किट होते हैं जहाँ पे मान लीजिए वहाँ स्पेस में रहेगा 20 साल एंड वहाँ पे कोई जाके उसको करेक्ट नहीं कर सकते हैं, तो वहाँ पे फेल्योर टॉलरेंट डिजाइन बहुत इंपॉर्टेंट है। और उसके बाद फेल सेफ डिजाइन, मतलब फेल मान लीजिए हो भी रहा है तो इस डायरेक्शन में फेल हो सर्किट जो जिसमें किसी को नुकसान ना हो। जैसे मान लीजिए कोई लिफ्ट है, मान लीजिए कि उसका फॉल्ट आया तो कम से कम वहीं पे धप करके नीचे ना गिर जाए, है ना। तो फेल उसको कहते फेल सेफ डिजाइन। सर्किट में फेल बट फेल का तो किसी को नुकसान नहीं होगा, इसे फेल होगा कोई नुकसान ना हो। तो दिस आर द डिफरेंट डिजाइन फिलोसफी व्हिच आर यूज्ड इन प्रैक्टिस। सो थैंक यू। और किसी का कुछ क्वेश्चन है तो पूछ सकते हैं। आई थिंक दिस इज एनफ। Okay, you can get my email. HN you can see from MNNIT website HNKR at मैं यहाँ पे लिखना भूल गया @MNNIT.ac.in. So in case of any queries you can consult me. Or these topics for the introduction actually I will recommend one book, Switching and Finite Automata Theory by Kohabi. This is a good book to start. Switching and Finite Automata Theory by Kohabi, Kohavi. इसका 3rd एडिशन टाटा मैकग्रो-हिल से पब्लिश्ड है। दिस बुक इज यूजफुल। वहाँ पे आपका ये फॉल्ट जो मैटर हमने डिस्कस किया मोस्टली आपको मिल जाएगा।
Any more questions from the participants? Hello. Any more questions from the participants? So there is a one question, sir, from the one of the participants. She is not presently. She is not present this time. She has messaged that question that is there any software for this, sir, where we can find out the faults in digital circuits? We can use any type of software.
Okay. No, actually the methods which we have discussed, है ना, so there is no ऐसा software. Or but these companies and MFs, they use some softwares, but they normally do not disclose those codes because they are application specific and for their product only. So open software is not. I don't think there is any software available commercially which can be directly used. But one can develop their own code. It is not difficult.
Sir, excuse me, sir.
Ah,
Sir, while doing test compression, that is for doing test compression, is there any software, sir, simulation software available?
for fault detection.
Sir, not fault detection, sir, test compression. To find a test compression ratio to analyze
Okay. No, I don't think there is any software.
Okay, so with the help of HDL programming code, shall we able to test, sir?
You can simulate it, but it is you can yes, by simulation you can test whether the circuit is operating correctly or not. But for this actually fault detection mechanism or number of tests, for these things actually there is no specific software.
Okay, sir. Sir, can you give me some idea about benchmark circuits, sir?
Benchmark circuits actually see the concept which I introduced in this lecture, है ना?
Okay, sir.
Actually ये क्या है कि these are not, this has been modified. This is just simply introductory concepts.
Yes, sir.
In fact, this fault table method which I discussed, it is not really used in this way.
Okay,
But it
sir.
is just for understanding. Actually, I discussed that this works in this way. Actually, there are many techniques. In fact, at the beginning, you can reduce the number of faults. What I considered that all lines are stuck at 0, stuck at 1. But there are some theories or some research development where there are using some properties, you can reduce it there itself. So those part actually I have not discussed in this.
Yes,
So
sir.
it is just introductory concept. I am not claiming that these are very advanced. These are just introductory concepts.
Okay,
And
sir.
it is still under development.
Okay, sir.
And research is going on in this area. This is a very potentially good research area.
Yes, sir.
Though I am not directly involved in this area, I teach this subject, but
Okay.
I have seen many work in this area, and still it is going on.
Okay, sir. Okay, sir. Thank you, sir.
Shushma ma'am, would you like to ask some question? Shushma ma'am?
Yes, sir.
Yes,
Good
ma'am.
afternoon, sir. Good afternoon, everyone.
Good afternoon.
Actually, in the context of the question just now that ma'am asked, I just wanted to tell you that many times it happens when the chip is under process. A few faults are there, and they are marked, means the manufacturer itself mark red. So when we program such ICs, we have to simply avoid those areas, those pins to be programmed. So right now, my question to Kar sir is, right now, is there any process or is there any provision to means can we repair these manufactured faults? Can we repair the faults which are there during the manufacturing, or we have to just leave that area? We can't program it.
No, I think both can be done. It depends which approach we should adopt. See, in case of during manufacturing, for example, suppose fabrication, which you are mentioning during IC
Yes.
fabrication, actually they are actually transistor. We just see that see ultimately during manufacturing is if the error occurs during manufacturing process, so we have to repair it. There is no other way, because we cannot manufacture faulty ICs. So during manufacturing, we have to repair it. Otherwise, it has no purpose. So that there are some methods which we have not discussed in this lecture.
Yes.
We have just introduced a stack open fault and stack with some
Yes, yes.
conduct. So that is actually they measure the gate and drain current, and just the.
No, in our means,
But
in our,
from applications point of view, suppose I have purchased something, and suppose if some person is not working, and still it is useful for me, so I am not going to repair it. I can use it. So actually, everything depends on situation. from applications point of view, users point of view, it may happen that he can leave that portion, the faulty
Yes,
portion of faulty
actually,
module.
Means for those experimental kits which we are using for the educational purpose,
Yes, we
the
can leave.
experimentation is very limited, sir.
Yes,
So
yes, yes, yes.
yes, so
Yes, we
means
can
when we
isolate
are
it.
yes, when we are performing our regular experiments, these problems do not occur. But when from research point of view, I just wanted to ask that right now it is not possible to fix the faults which are occurring during the manufacturing.
No, manufacturing, suppose जो manufacturing company manufacture which they have to repair it.
Yes,
They
yes,
actually repair means they will take care of that person, that
yes.
such that fault does not occur.
Okay.
Then only that IC will be successful. Otherwise,
Yes.
है ना? So during manufacturing they take care of it. They test it and they find fault. They can redesign and remanufacture.
Yes.
It happens.
Thank you, sir.
Okay, thank you.
Thank you, Wim. Thank you, sir. It was a very nice session. It is very rarely we used to find the fault detection techniques in the digital circuits. That the topic you have chosen for the presentation. It is totally practical session that you put it on the online mode. It was very a tough job, but thank you, sir, for that. And really, the session was very interesting because detecting hazards and faults and testing also of the digital circuits in mostly in the very complex circuits it's a very tough job. Basically, we go ahead for the replacement, but still after this session we will have an option to for the testing and the detections also, sir. Thank you, sir.
Thank you. Thank you.
Thank you, sir. Okay, sir. Thank you, sir.
Thank you.